Howdy there, Mr. Sutton here with the AB Calculus 4-5 Extra Practice number 2 solutions on points of inflection. On this problem, we want the coordinates of the inflection point for y equals x plus 1 arctan of x. So in order to get inflection points, we need to figure out the second derivative and get some critical values for that. So let's start with the first derivative. First derivative is going to require a product rule. So let me get out the box and ribbon here. We've got products of x plus 1 and arctan of x, and the derivatives of those are going to be 1, and this is going to be 1 over x squared plus 1. So multiplying that out with the ribbon, we've got arctan of x plus, this will be x plus 1 over x squared plus 1. So the good news is we just did y prime. The bad news is we got to do y double prime in order to actually figure out the inflection point. So let's go again. We've got derivative of arctan, which is 1 over x squared plus 1, so we just got that. This next one is going to require the quotient rule, so let me set up a box and ribbon for that one. We've got a numerator of x plus 1, denominator of x squared plus 1, and the derivatives of those, which are 1 and 2x. So now the format for the quotient rule, we're going to have a big fraction here. And this is essentially going to be u prime v minus uv prime all over v squared. So I'm going to use the ribbon in my box to get that the way I want it. So we're going to have going this way x squared plus 1. And then going the other way, I'm just going to distribute as I go. So this is going to be 2x squared, or actually minus 2x squared, because we're subtracting uv prime, minus 2x. All of that over x squared plus 1, the quantity squared. Okay, so this is still a bit of a mess. I'm going to combine this into one fraction so that I can more easily analyze where it is either 0 or undefined, getting those critical values. So to get this into one fraction, I'm going to need a common denominator. The good news is I'm almost there. I have an x squared plus 1 over here, and I have, well, 2 of those over here. So I just need to multiply this first fraction by x squared plus 1 over itself. That'll give me an x squared plus 1 squared in the denominator and just an x squared plus 1 in the numerator. Now I can just add these numerators together. So I have an x squared, another x squared, that's 2x squared, minus 2x squared, so those x squareds actually cancel out completely. And I have a 1 plus a 1, which is a 2, and then this negative 2x is just kind of by itself. So we have 2 minus 2x in the numerator, and we have that common denominator as well to go with the 2 minus 2x. So now I want to know where this thing either equals 0 or is undefined. Taking a look at where it equals 0, we're going to have to look at the numerator. So 2 minus 2x needs to equal 0. And that's going to happen if I add 2x and divide by 2. That's going to happen at x equals 1. Now there's no place to make this undefined because this x squared is never going to be negative, so you can't cancel out this 1 to get a 0 down here. So this is our only critical value. Now we're going to put this on a number line and do some sign analysis. So here I go with a y double prime number line. I have my sole critical value on here. I went through a lot to get that critical value. So now let's test a number that's less than 1, like 0. And I'm going to try it out in this version of y double prime over here, this reduced simplified fraction. So the denominator, the good news is the denominator is always going to be positive because you're squaring stuff here. So really the only thing that makes a difference on the sign is the numerator. If I plug 0 into the numerator, I've essentially got 2 minus 0, which is a positive. And then something bigger than 1, let's try 2. So now I'm doing 2 minus 4 basically, which is negative. And because we have a change in sign at x equals 1, because y double prime changes sign there, that means that y has a point of inflection at x equals 1. So that's good. That tells us that the x value is 1, but if you look at the answer choices, there are 2 answer choices with an x value of 1. So we also have to plug this back in to the original function to figure out what the y value is. So that's going to be, let's see here, 1 plus 1 times arctan of 1. Arctan of 1, that's going to be pi over 4. So this is really 2 times pi over 4, which comes out to pi over 2. So we have 1 comma pi over 2, which is going to give us choice E. For this calculator-based problem, I'm given 3 twice differentiable functions, f, g, and h, and actually I'm given their second derivatives. We want to know which of these graphs have exactly 2 points of inflection. So what that means, if you have 2 points of inflection, that means that the double prime, the second derivative, is going to change sign exactly twice. No more, no less. So all we have to really do is graph these out and see which ones have exactly 2 sign changes. All right, well, to do this, let me go to my y equals on my calculator. So in my y equals, in my y1, I'm putting f double prime, and that took a little bit to write out, but I got it in there. Now I'm going to write the other 2. Now, I'm going to be kind of clever about this, because if you look at g double prime, it's exactly the same as f double prime, except you're adding 1 at the end. It's basically a small shift in f double prime. So I'm going to do alpha trace, call up y1, and then I'm just going to do plus 1. And then for the h double prime function, it's basically f prime minus 1, or f double prime minus 1. So I'm going to do, again, alpha trace y1, and I'm just going to subtract 1. So we've got f, g, and h double prime. All right, now that I've got all those entered in there, I'm going to graph them, but I don't want to graph them all at the same time. So just make sure you deselect the ones you don't want to look at. First, we'll look at f double prime. So going back to my grapher, I'm going to deselect y3 and y2. And for my window, let me just do zoom 4. So there we go. So there's f double prime. And now I'm going to take a look at what g double prime looks like. So going back to my y equals, I will deselect f and select g, and then graph that out. There's g. So far, f double prime crossed twice, it looked like, and g double prime also looks like it's crossing twice. Let's look at h double prime. So going back to y equals one more time, I'm going to deselect g and select h double prime and graph that. And that one crosses, let's see, 1, 2, 3, 4, well, more than twice. So there's h prime double prime again. So taking a look at these, only f double prime and g double prime cross exactly twice. Therefore, we're going to pick answer choice C. On this one, I want to know the x-coordinate of the point of inflection for this polynomial. So let me start by getting the second derivative of this. I'm going to do some sign analysis on critical values for y double prime, and that'll teach me about the point of inflection. So first derivative, y prime, that's going to be, let's see, 3 times a third cancels, so that's just 1x squared plus 10x. And then the second derivative, that's going to be 2x plus 10. So I want to set that equal to 0 and solve for critical values. If I subtract 10 and divide by 2, that's going to be negative 5. So let me do some sign analysis on that. And I mean, we don't have any other critical values, and there's no answer choice for there is no point of inflection, so negative 5 is probably the answer. But let's just double check. So there's y double prime number line here, negative 5. Checking a number less than negative 5, like negative 6. If I plug that into y double prime here, that's going to be negative 12 plus 10, which is a negative. And then something bigger than negative 5, I'll go with 0. So that's just going to be 0 plus 10, which is a positive. Since y double prime changes sign at x equals negative 5, y has a point of inflection at y equals negative 5. So we can confidently pick choice D. On this problem, f is a function that's twice differentiable on negative 2 to 2, and has some conditions given in this table here for various intervals. We're also told that f of x and f of negative x are the same thing, which is kind of interesting. So we want x-coordinates of points of inflection for our graph of f on negative 2 to 2. So we know for points of inflection, we're looking to see sign changes in the second derivative. And taking a look at the graph, here's f double prime. We notice that at x equals 1, the sign of f double prime is changing from negative to positive. Since f double prime changes sign at x equals 1, we know for sure that there is a point of inflection at x equals 1. Well, we know that there's a point to begin with because they said the function's twice differentiable. So that means that if nothing else, the function's going to have to exist at x equals 1. All right, so that's one of the answer choices. Choice B. However, there is one other piece of information we need to consider. They said that f of x equals f of negative x. So what is that all about? Well, that's another way of saying that the graph is symmetrical over the y-axis, because you're basically saying that when you plug in 1 and negative 1, you get the same thing, the same output. So here's where this is important. If your graph is symmetrical over the y-axis, then everything that is happening behavior-wise for the graph on the right side of the y-axis has a mirror image happening on the left side. So if you have a point of inflection at x equals positive 1, you're going to have a point of inflection at x equals negative 1 because, again, this graph is symmetrical over the y-axis. So that means we actually have to pick answer choice D. For this one, we have the graph of the function y equals x cubed plus 6x squared plus 7x minus 2 cosine of x, so almost a polynomial. They're saying that this changes concavity when x equals which of these numbers? So if I want to know about concavity, I need to take a look at what y double prime is doing. And this is a calculator question, but I need to know what y double prime looks like. So that requires two derivatives. First derivative, we've got 3x squared plus 12x plus 7. And then this is going to be plus 2 sine of x. Now for the second derivative, that's going to be 6x plus 12. 7 just becomes 0 there. And this next one is going to be plus 2 cosine of x. Let's go ahead and graph that now to see where we are changing sign. So I've entered this y double prime function into my y equals as y1. But now for the interval, what should I use? Well, I'm going to use a window, just looking at my answer choices. They're all between basically negative 1.5 and 2.5. I'm just going to go, let's be a little conservative here. Let's do from negative 1 to negative 2.5. And that ought to definitely cover us. And let me zoom fit this thing. And window range. What's wrong with my window range? Oh, we have to have negative 2.5 first. There we go. Okay. So now let's try zoom fit. Can't put things out of order. The calculator knows better. So there is my graph between negative 2.5 and negative 1. And we see here that we're changing the sign of y double prime at this spot. Let me do second trace and then zeros to see which one that is. So let's move my spider a little bit to the left, a little bit to the right. Enter. That's about negative 1.894. So there's that graph again. There's that number. And that's going to be answer choice D. For this problem, I've got this expression in x plus k over x, and I want to know what k value is going to give this thing a relative max at x equals negative 2. Well, to have a relative max, that means that the derivative of this thing, when I plug negative 2 into it, ought to either be 0 or undefined. So let's figure out what the derivative is, and we'll go from there. First, let me rewrite this. I'm going to write this as f of x equals x plus kx to the negative 1, just to make it a little easier to take the derivative. And now f prime is going to be 1 minus kx to the negative 2. So there's my f prime. Now, when I plug negative 2 into this, I ought to get an output of 0 if I have a relative max. So let me go ahead and give that a shot. So plugging in negative 2 for x, again, the output should be 0. And this is really, this is k times negative, or k over 2, negative 2 to the second power. This is really 1 minus 1/4 k. So let me just add that 1/4 k to the other side of the equation. And now solving this by multiplying by 4, I see that my k value is going to be 4. So, I mean, I don't know for sure that this is the relative max value that they were looking for, because for all we know, this thing should have been undefined, but it is a k value that we can look at. We also have an answer choice for none of these. So I'm thinking at this point, we're either going to be going with k equals 4 or none of these. To prove that this actually gives us a relative max, we need to do a little more work though. And probably the easiest way to proceed on this one is to rewrite f prime with the k value that we just found, so 1 minus 4x to the negative 2, and then just run the second derivative test on this thing at negative 2 to see if it's a max or a min. So second derivative, pretty easy to take on this. That's just going to, this 1 goes to 0, and this is going to be 8x to the negative 3. So running the second derivative test on this, I'm just going to plug in negative 2 again. So that's going to be 8 over negative 2 to the third power if I change back into fraction form. And this is going to come out to negative 1, which most importantly is a negative number. If the second derivative is negative and the first derivative is 0, that means that we are at the top of a frown, that we just found a relative max at x equals negative 2 for k equals 4. So we can confidently choose D on this one, and now we've proven it. For this free response problem, we're given this curve up here, and our first step, our first part, is we want to show that the derivative of this thing is this fraction here. So basically, they're just asking you to prove that this is true, and the fastest way to do it is just to take the derivative of this thing and show that you get this thing. So to do that, because it's difficult, actually impossible to isolate y, we are going to have to use implicit differentiation. So we're going to just take derivatives, and whenever we take the derivative of something with a y, we're going to use the chain rule and treat y as an inner function of x. We're going to multiply that by a tail of y prime, or dy over dx. So the derivative then of x squared is going to be 2x. And then for 4y squared, that's going to be 8y times dy over dx. There's that chain rule because y is its own function. Equals, well, 7 is just going to become 0 when you take that derivative. 3xy is going to require a product rule. So we'll set up the box and ribbon to help us with that. We need u prime v plus uv prime coming out of this. So I've got my 3x factor up here, and we'll put the y over in this box. The derivatives of those, u prime and v prime, we've got 3. And derivative of y is going to be dy over dx. Using the ribbon to multiply this out, this is going to be an equals, because we're on the other side of the equation, and we're going to get 3y plus 3x dy over dx. At this point, I have to get all the dy over dx's on one side and everything that's not dy over dx on the other side. So this 8y dy over dx can stay on the left. We're going to subtract this 3x dy over dx to get it over there. And then we're going to move the 2x over to the right side. And the 3y is already there, so we can just subtract 2x from 3y, and there we go. Now, the reason I didn't bother writing negative 2x plus 3y is, I'm looking at my answer, kind of thinking ahead. I want to get exactly this in my work down here. So now, on the left side, we're not quite there yet. I need to factor out dy over dx. That leaves me with 8y minus 3x in the parentheses. And then if I divide both sides by that parentheses, I get exactly what I wanted for part A. For this problem, I'm trying to show there's a point P with x-coordinate 3 at which the line tangent to the curve at this point is horizontal, and then find the y-coordinate. Now they did these things in a different order than I'm going to do them, or they asked them in a different order. I'm actually going to answer the second question first. So what I'm going to do, in order for this tangent line to be horizontal, the derivative has to equal 0 at this x-coordinate 3. So I'm going to take the derivative from part A, that was 3y minus 2x over 8y minus 3x. I'm going to plug 3 into this thing, and I'm going to figure out what y value is going to make all of this come out to 0. Because again, 0 means you have a horizontal slope, horizontal tangent line. So if all this stuff has to equal 0, that means that the numerator, 3y minus 6, has to equal 0. And if I add 6 and divide by 3, that means my y value must be 2. Doing a quick mental check, if I plug 2 in for y in the denominator, I'm not getting 0 down there, so that's a good thing. So this is good. I've got a y value. I've got a point. That doesn't necessarily mean, though, that this p point that I just found is on the curve itself, which is part of this problem. all I've shown is that when I plug in 3 for x and 2 for y, that makes this derivative come out to 0. But the derivative doesn't tell you where the original curve is in space. All the derivative tells you is what the curve is doing in terms of increasing versus decreasing. So to prove that the point 3, 2 is even on the original curve, I actually need to plug it into the original equation here and make sure that it comes out the same on both sides. So doing that, I've got an x value of 3, so that's going to be 3 squared, plus 4 times the y value 2 squared equals 7, plus this is going to be 3 times the x value 3 times the y value 2. And let's just make sure this comes out the same on both sides. I want to emphasize this is necessary because just solving for y doesn't prove anything about the original function. It just proves something about the derivative. So now on the left side here we've got 9 plus 16, which is 25. On the right side we've got 7 plus 18, which is also 25. Once you've shown that you get the same thing on both sides, you've proven that you've got the y value you needed. For this last part of the problem, they want us to find the second derivative at point P, and then this one, they want us to tell them if the curve has a local max, min, or neither at point P. So first things first, let's find the second derivative, and before I can do that, let me rewrite the first derivative. Here it is again from part A, 3y minus 2x over 8y minus 3x. They gave us that. And then it's also probably worth noting that point P was 3, 2. That was from part B that we found that. So in order to take the derivative of this, I'm going to need the quotient rule, u prime v minus uv prime over v squared. So let me set up the box and ribbon to help me take this second derivative. So over here, we've got the numerator, 3y minus 2x. Denominator is 8y minus 3x. And I'm still going to have to implicitly differentiate here, just like I did to prove this first derivative. Because again, y is still an inner function of x. Can't really isolate the y. So this is going to be 3 dy over dx minus 2. And this derivative for this one is going to be 8 dy over dx minus 3. Before I use the ribbon to put all this back together and then plug in 3, 2, I'm actually going to plug in 3, 2 inside the box. Then I'll put it all together out here. So I've got an x value of 3. I've got a y value of 2, and you'll notice if I'm plugging stuff in here to get numbers, I need to plug in something for dy over dx. Well, what's dy over dx? In part B, we showed that when you have this point 3, 2, you've got a horizontal tangent line there. That means dy over dx has a value of 0, and that was part of what we did in part B. So let's go ahead and plug all this in inside the box. So given all these parameters, this is going to be 3 times 2 minus 2 times 3, so that's 6 minus 6, which is 0. Over here, I've got 8 times 2, which is 16, minus 3 times 3, which is 9. 16 minus 9 is 7. Down here, this is going to be 3 times 0, which is going to 0 out, so that's just negative 2. This is 8 times 0, which is gone, so just negative 3. And now multiplying it together with the ribbon here, I've got negative 2 times 7 minus 0 times negative 3. So that's plus 0 times 3. I mean, it's just 0 one way or another, all over 7 squared. So this comes out to negative 14 over 49, which I can reduce to negative 2 over 7. Now, let's follow this up with the next part of the question here. Does the curve have a local max, a local min, or neither? So you've already figured out that you have a critical value at 3, 2 because you had a first derivative of 0. That's great. In order to figure out if it's a local max or min, there's two ways to do that. If you're trying to use the first derivative test on this, that's going to be kind of difficult because if you're doing sign analysis, I mean, normally we would pick, a number before this and after this point. The trouble is your derivative uses both x and y values. So how can you even really think about plugging in something before 3, 2 and after 3, 2? I mean, before and after, you're talking like a two-dimensional before and after. Totally crazy. So a much easier way to do this is to use the second derivative test. You've already established that you have a first derivative value of 0. All you have to do is look at the sign of the second derivative. Well, here's your second derivative at 3, 2. We just figured out that this was negative. Therefore, since the first derivative is 0 and the second derivative is negative, that means that we are at the top of a frown. We are at the top of concave down, so we are at a local max.